Exit code 13 is not a crash. It is a forced termination via SIGKILL Signal 9, which is 128 plus 9. This means the container did not exit gracefully, it was murdered by the host kernel. The primary suspect is the Linux out-of-memory killer, or killer. To confirm this diagnosis immediately, check the host system logs using the command dmesg grep ii killer. Look specifically for entries listing the process ID and the Cgroup path associated with the terminated container. If the killer is the culprit, the log entry will explicitly detail the memory pressure and the process chosen for termination. This correlation between the host kernel log and the container identifier is the fastest path to diagnosis. Do not waste time checking application logs first. The application received no chance to log its demise before termination. The killer output in dmesg provides the process ID, or PID, that was killed. This PID is the process ID inside the host namespace, not the container namespace. To link this back to the specific container, use the command docker inspect container ID format : state : PID. Match this host PID against the victim PID listed in the kernel logs. If they align, the diagnosis is confirmed: resource exhaustion. If the PID does not align, check for manual docker kill-SIGKILL operations or external orchestration system terminations. However, 137 almost always points to If the host PID matches, the next step is analyzing the resource constraints that were violated. Docker uses Linux control groups, or Cgroups, to enforce resource limits. The memory limit for your container is defined in the Cgroup file system, typically under /sys/fs/cgroup/memory/docker/container ID/memory.limit invites. Access this file from the host to verify the hard limit imposed. Compare this limit against the actual usage reported in /sys/fs/cgroup/memory/docker/container ID/memory.usage invites. A critical metric is memory.failCount, which increments every time the container attempts to allocate memory beyond its limit. A high failure count confirms the container was constantly hitting its ceiling before the killer intervened. If the limit is 0, the container is unbounded, meaning the host itself is under severe memory pressure. If the container is consistently hitting its limit, the immediate fix is increasing the allocated memory. When running Docker directly, use the -m flag, for example, docker run -2g. If using Docker Compose, define the mem limit parameter under the service configuration, specifying values like 2048M or 2G. Remember that the default Docker memory limit is often unbounded, relying solely on host resources, which makes the killer highly aggressive. Explicitly setting a limit, even if higher, provides predictability and prevents the container from consuming the entire host memory pool. Always allocate slightly more than the peak observed usage to prevent transient spikes from triggering termination.
Exit code 137 can also be triggered if the container exhausts both physical memory and the configured swap space. By default, Docker containers often inherit the host's swap settings, but this behavior can be explicitly controlled. Use the --memory-swap flag in Docker run. Setting --memory-swap to the same value as --memory effectively disables swap for that container. If you set --memory1g and --memory-swap2g, the container gets 1 GB of physical memory and 1 GB of swap. Carefully evaluate if your application benefits from swap. For high-performance databases, swap is detrimental due to latency, but for batch processing, swap might prevent a 137 exit by allowing temporary memory overflow. For Java applications, the container memory limit is often irrelevant if the Java Virtual Machine, or JVM, is not configured correctly. The JVM defaults often assume a bare metal environment, allocating up to 1/4 of the host memory for the heap, ignoring the container's Cgroup limits. This mismatch guarantees OOM termination. Set the explicit maximum heap size using the -xmx flag, ensuring it is significantly less than the container's memory limit. A safe margin is typically 20% below the Cgroup limit to account for non-heap memory usage like thread stacks, garbage collection overhead, and native libraries. Failing to constrain the heap size is the most common cause of 137 in Java containers. Node.js applications running V8 also require specific tuning to respect container boundaries. V8's garbage collector manages the heap, and its default behavior can lead to memory spikes exceeding the container limit. Control the maximum old space size using the --max old space size flag. This value should be set in megabytes and must be constrained relative to the container's Cgroup limit. Failure to set this results in V8 attempting to utilize available system memory, which, in a constrained container environment, leads directly to the OOM killer intervention and the resulting 137 exit code. For modern Node.js versions, consider using the --experimental worker flag to improve memory awareness within Cgroups. If increasing limits only delays the 137 exit, the root cause is likely a memory leak within the application code. Implement continuous profiling. Tools like Java Flight Recorder for Java applications or heap snapshots in Node.js are essential. Capture memory usage over time under typical load conditions. Look for objects that are allocated but never released, leading to a steady, non-decreasing memory footprint that eventually breaches the cgroup limit. Address the leak by optimizing object lifecycle management or correcting reference retention, rather than masking the issue with larger container limits. Profiling provides the only verifiable path to long-term stability. In orchestrated environments like Kubernetes or Amazon Elastic Container Service, prevention relies on setting accurate resource requests and limits. In Kubernetes, define resources.limits.memory in the pod specification. This value directly translates to the cgroup limit enforced by the container runtime. Crucially, set resources.requests.memory lower than the limit. The request ensures the scheduler places the pod on a node with sufficient guaranteed capacity, while the limit prevents the container from exceeding its allocated budget. Setting the limit ensures a predictable 137 exit instead of destabilizing the entire node, which is the worst-case scenario when limits are omitted.